Hello Performance Ninjas and welcome to the Compiler Intrinsics 1 lab assignment. There is a certain class of applications that have very few hotspots. You can imagine some scientific application which crunches numbers in a tight loop. The code outside this loop can be very slow, but it doesn't matter, since all we need to do is to optimize this particular loop. Unfortunately, compilers do not always do what we want in terms of generated code in those hot places. For specialized algorithms, sometimes we can come up with a clever solution which will generate better sequence of instructions that compiler can offer. It can be very hard or even impossible to make the compiler generate the desired assembly code using standard constructs of the C and C++ languages. But hopefully, we can force compiler to generate particular assembly instructions without writing inline assembly. To achieve that, one can use compiler intrinsics, which are special functions that compiler translates into specific assembly instructions. Intrinsics provide the same benefit as inline assembly, but also they somewhat improve code readability, allow compiler type checking, assist instruction scheduling, and help reduce debugging. Consider this simple piece of code, and intrinsics are highlighted in yellow. And when compiler sees this code, it pretty much has no choice but to generate the assembly instructions that I show on the right. All the modern compilers support this feature, although not all instructions have direct compiler intrinsics equivalent. The list of all available compiler intrinsics for the x86 platform can be found in Intel Intrinsics Guide. And here I show a similar guide for the ARM platform. There are a few caveats I want to make when you use compiler intrinsics. First, when you write standard C/C++ code and rely on compiler optimizations, it is compiler responsibility to ensure validity of the transformation that it makes. For example, when auto-vectorizing the code, compiler will insert runtime checks to make sure there are enough elements to feed vector units, there is no pointer aliasing and so on. But when you are using compiler intrinsics, you have to take care of all the safety aspects by yourself. Secondly, since compiler intrinsics map to assembly instructions, they are not portable. When you write the code using non-portable platform-specific intrinsics, you should also provide a fallback option for the other architectures. And finally, the code that uses compiler intrinsics is less readable and even sometimes resembles assembly code. If you will check some real-world examples, usually you will find different code paths for different platforms and ISAs, like SSE, AVX2, AVX512, ARM Neon, and it could be very hard to read. So, given all the caveats mentioned above, I recommend to mostly write standard C/C++ code and rely on compiler optimizations. Use intrinsics only when necessary. It should be your last resort when you cannot convey your intention by adjusting the code or using pragmas and other compiler hints. Sometimes we can teach compiler to recognize a certain code pattern and generate a better machine code, but in general it is a hard problem to solve. So for now, compiler intrinsics are here to stay, and in this lab, I will show you one such example. In this lab, we have image smoothing algorithm. Here is the hot loop, which is unfortunately not vectorized by the Clang 12 compiler. As before, there are many ways how you can check that. One of the ways I show here is to look into the compiler optimization reports. Another way is to look into the profile. And here you can see that for our loop, only the scalar instructions were generated. And so to solve this lab, you have to think how you can rewrite this loop in a SIMD fashion using compiler intrinsics. So yeah, that's it for this video. You can now go to the lab assignment and try to improve performance of the code.